I have one advice which got me many enemies, and this is rebel against your professors.
Rebel against
Okay?
professors. Okay.
Yes. I mean, don't take their word as the last to replace explanation. If you insist on understanding things your way, then don't take their word to be their authority to be a replacement for explanation. You need to understand it your way. And I grew up with that kind of chutzpah, with that kind of audacity to demand understanding in real time. And people here are too polite to professors.
Judea Pearl, it's a pleasure to having you on the show.
It's great to be here, Adil.
It's our pleasure. So,
Thank you for having me.
as you know, Judea, academia is a perfect place to sharpen our research abilities towards excellence. However, it tends to be less helpful, I would say, about mentoring and thinking about our wider context, where research ideas grow. So this conversation is going to be about a little bit of your perspective, both in terms of research topics, but also your macro, micro strategies as we move forward in this field of causal inference in particular, which is one of your main signums. Judea Pearl, you are the Chancellor's Professor of Computer Science and Statistics at UCLA. You are also a distinguished visiting professor at Technion in Israel Institute of Technology. You received your Ph.D. in electrical engineering from Polytechnic Institute of Brooklyn, 1965. You are the director of the Cognitive Systems Laboratory at UCLA. You are one of the founding editors of the Journal of Causal Inference, member of many boards, among them the National Academy of Sciences and the National Academy of Engineering. You are also have received many awards for your work, amongst them the Turing Award, which is widely considered as a Nobel Prize in computer science, the Lakatos Award in philosophy of science, the Allen Newell Award, the Benjamin Franklin Medal, amongst many different types of awards that you've received. You've published many articles and books, amongst them the book of Why, that I've actually read twice, listened to it in audible once and read it in physical format after that. So it's a true pleasure having you here, Judea. And really my first question to you is, looking at your publication record, is how you've been targeting, I mean, your PhD was in superconductivity in the 1960s. But the critical piece that I think is really important to bring forth here is that how you've been managing to balance philosophy of science, perhaps more particularly, and computer science as a discipline. They are quite disparate, right, in terms of what they do, how they think, how you bring forth the level of formalism as well. So how do you bring together such two disparate disciplines?
I would say it's a combination of two things. One, my exposure to computer science in the early 1960s, and the second was my upbringing in Israel. When I arrived here at the United States and I got a job in a computer science group in RCA laboratory in Princeton, New Jersey, we worked on memory devices, hardware. Yeah, superconductivity was a search result of a search for physical phenomena that exhibit memory. Why memory? Because everybody knew that computers are going to take over.
Yeah.
And the memory devices were slow and unreliable computer magnetic cores. So everybody understood that the days of magnetic cores are numbered. But the spirit throughout that activity, although we were dealing with hardware, was a conviction of everybody in the group that computers are here to take over and eventually will be able to emulate most of the functions that human beings do. That was the spirit. I'm talking about the 1962, 1963.
Yeah, before Macintosh, before IBM was around, but before all kinds of PCs as we have right now. So it's a different world entirely.
The only programming language I remember at that time was Fortran.
Okay.
That was So that is that was one component. The spirit that I found here in America laboratory. And we started thinking about various means of emulating memory, perceptions, associative memories, reasoning. That was in the air. So everybody had ideas about it. So that was one of the components that brought me into that thinking. And the second one was my upbringing in Israel was immersed in good scientific foundation of history of science. We learn history of science quite well, primarily directed into electrical engineering, of course, electromagnetic wave, Faraday, Maxwell, Galileo and Newton. So, but we got a very good exposure to the lives and times of the inventors or the theory makers of that time.
That's just to interrupt you there, Judea. It's actually what we're doing now. We're getting to know you, the inventor.
Yeah, but I'm not a Galileo. I'm just here. But it helps. I think it does. For me, the idea that I'll follow the steps of Faraday is a tremendous excitement. I have Faraday book if you want to see it.
I mean, one of the things, and you should bring this to the audience, Judea, please. You just showed me one of the originals from a book that Bernoulli wrote in 1713. If you have it there, please.
Well, here it is. Yes, that's Bernoulli in Basel. Art Conjectuandi.
That's amazing. Look at that.
The art of making conjectures.
That's amazing. Yeah, the background filter is setting in, but we see it now. That's very good. Looking very amazing.
Okay.
So
I am inspired by the great scientists and their lives, not only their work, but also their lives and the times in which they live, the ideas that they entertained, the options that they have, and the eventually direction they took, and their enemies too, and the debate that they had among themselves. Okay,
right.
I'm inspired by that.
Can you give us an example of how, for example, reading about Bernoulli or any of the great other philosophers have helped you? What kind of a element in their thinking have sparked a new idea in yours? If you have an example, that would be fantastic.
Faraday, for instance, he came out with the idea of a field that you don't have action in the distance. If the magnet moves, it moves not because there is another magnet in the distance, which pulls it, but because there is a local field in the vicinity of this magnet.
Oh yeah.
Okay, so it was just a concept which nobody thought about it earlier. But this simple concept that there is a field here, in which the magnet is immersed, and that field is pushing the magnet one way or the other. Right? And Maxwell took it seriously, and wrote the 4 equations that are called Maxwell equations. And now this Maxwell equation, and this is very important, Maxwell was an armchair physicist. He looked at the equation and he looked at it and said, well, it looked like a wave. Oh, if it's a wave, maybe I can calculate the velocity of the wave. Okay? And he put in the right constant, the epsilon and the mu, the permittivity.
Yeah.
And lo and behold, what did he get? The velocity of light.
Yeah.
300,000 kilometers per second.
Yeah.
And he said, wow, that means that light is nothing but electromagnetic wave. This was an armchair discovery based on equation. And that blew me off. Yeah. The idea that you can get a conjecture about the physical world by playing around with equation.
Yeah. And that has inspired your work in causal inference in some particular way. I mean, I'm thinking about the field example, the metaphor there. You're thinking the directed cyclical graphs where you can think about a random variable situated, and then we think about what's going on around that random variable, almost like a field, right? What comes into a random variable, what goes out, almost like this Markov blanket.
Perhaps you're right, yes, because the idea there that variables in the world are listening to others.
Exactly.
Listening.
Yeah.
And the idea of listening is the metaphor
of a field,
which drives everything we know about causality.
Yeah, exactly. So maybe there's a huge resemblance there in ideas.
There is, absolutely, yes. The reason that things are happening is because this battle, or the temperature of this battle, listens to the variables around it.
Exactly.
Including the speed of the molecules from my mouth and the radiation from this light bulb, and makes a decision. I'm going to take upon myself the temperature of 36 degrees centigrade exactly, and not any other.
Right.
Deterministic. Okay. So this idea of looking at the world as a society in which everyone listens to its neighbors.
Yeah.
Probably it came from Faraday and Maxwell.
There we go. I think we've solved that one. We know where that came from in your stream of ideas. So, Judea, how come that you selected computer science and engineering and not philosophy? So, I mean, you are inspired by these ideas, but also that you have a philosophical tone in your books that few thinkers have in computer science. You were open for this, what we would call maybe a fluffiness of ideas in philosophy that is hard to pin down for a mathematician and computer scientist. So tell us a little bit about your choice of engineering and computer science.
I was a computer scientist. I was first working on hardware and memories, and then I worked on pattern recognition and compression of images. I was a computer scientist.
Yeah. But I mean, before that, even before that, Judea, even before that.
No, I didn't think about philosophy.
Oh, I see.
Before 1970.
I see. Okay. So first came engineering, and then you started to become
more. All right. When I came to UCLA, I started teaching decision analysis. And that brought me into problems in philosophy.
I see.
Knowledge, minimax, Bayesian inference, decision making, utility theory. I started reading seriously all the literature on decision making, and it brought me into in philosophy.
Right.
Now I have also a theory that everybody in computer science is amateur philosophy. By the way, everybody in statistics is also amateur philosophy because they are dealing with data, and the data is supposed to be the source of all our knowledge.
Yeah.
So most statisticians think that they are doing philosophy of science, and they know all about philosophy of science. They can talk about induction, deduction, big deal. Well, it's true, but we, computer science, are true philosophers of science. And statisticians, I'm not kidding.
Expand a little bit on that. That's very good. So let's see what we can unpack that a little bit. So what you're saying here is that there's because we deal with data is very messy. I mean, it has also social side, right? where data comes from, it can be biased in many ways. It's sort of recording, measuring different processes. It could be a physical system, it could be a social system. But so expand a little bit on that idea. What's the amateurness in the philosophy of say, if you're a statistician versus a professional philosopher in this sense?
Okay, the mistake of the statistician is that data is a sort of our knowledge, which is not. It's data plus experiments plus I have to go to the ladder of science, the ladder of causation. This is the knowledge that we are after. Data is just simple one layer, which doesn't tell us about the making of the world. So the statisticians are handicapped to begin with. They think that they are doing philosophy of science because all knowledge comes from data. So which means the language of data, which is probability theory, is going to lead them into problems of philosophy of science. But it cannot lead them, because this is not the kind of knowledge we are seeking. We are seeking understanding of the making of the world, and which you cannot express in the language of statistics.
So what's the reason, do you think, today that if that's the case, that statisticians is locked into overthinking data? What philosophy has influenced them in the past to actually then go this path of overfitting to the data being knowledge versus theory? What's your sense here?
It comes from the British empiricist philosopher, from John Locke and David Hume, but mainly John Locke, who made it very clear that all knowledge comes from the senses. And here statisticians are in charge of the observational data, namely they are in charge of the source of our knowledge. Therefore, they saw themselves as heirs to John Locke, responsible for answering the question that he posed, namely, how do we know that what we know is true? How do we collect data? What does it mean to understand? But they were handicapped to begin with.
Interesting. So that's really fascinating. So, and for those who doesn't know, I mean, David Hume is one of the pioneers, if you like, of empiricism and later also positivism. That's only what we can see is really a foundation, can be a foundation for knowledge, right? And there are different versions of that, of how stringent you can go, and therefore, for example, Freudian theory cannot be scientific, because Freud talked about things that cannot be observed, and so from a positivistic perspective, Freud, for example, Freudian theory is not considered to be science, and so where do you see yourself in this debate? I mean, there's also the Kantian version where they talk about transcendental reality, where there are things that cannot be seen.
I can't read Kant.
You cannot read it. Why?
I don't understand it. It's too speculative.
Yeah.
It's a different language. Most of philosophers have been doing, they raise questions which I cannot understand. With the exception of few, like Locke, Berkeley, Hume, the empiricists, Bacon, I understand what they say, but the philosophers were also handicapped because their arsenal of metaphors was limited. Look at Kant. Kant couldn't quite reconcile the duality question. Here we have the question of how do I know that I exist? Okay? If I think, but his model of thinking was gears that rotates.
Yeah.
Why? Because he didn't have any other input-output device that he could use to explain the making of the mind. The only input-output device he had is rotating gears. He didn't have even electric circuit, which we call AND on OR gates. He didn't have that. Okay?
Right.
We today have a computer, much richer arsenal of metaphors.
Right.
So for us, we don't have to say the gears rotate inside to explain thinking. We can say the The guy computes. Therefore,
There he is.
I say I can program. Therefore, I understand.
Right. And so, interestingly, I mean, where do you stand in this landscape of philosophy or philosophy of science today in terms of causal philosophy? I mean, you have developed a foundational formalistic view of how to perceive causality in computer science and beyond. But in terms of the philosophy of causal thinking, I mean, there are several philosophies. I mean, I'm not talking about the potential outcome or anything like that. More in terms of the Humean version, the Kantian version, and realist. I mean, there's so many versions of causal inference. Do you have
only one version? It's only one version.
Talk about that.
There's one version and some imitations.
Let's talk about that.
Okay. So the version that I see is you're trying to reach an understanding of the world. And I define understanding very formally and very clearly. An agent is said to understand a domain if the agent is capable of answering questions on 3 levels: predictions, intervention, and counterfactuals. Very clear. Okay? Any machine, program, robot that can answer these questions, I'll say he or she understands the domain. Now, if you define it that way, you have to ground it in at least one model that exhibit such an understanding. Okay, I have a model, the SCM, structural causal model, which algorithmically I can show algorithmically answer questions in all 3 levels. Moreover, we have now a theory which tells us what can and what cannot be answered in any one level, what source of data is needed, what assumptions are needed to answer questions in each of these layers.
Right.
Done. In my life, or in my understanding as a computer scientist, once we have a theory, we have semantic, we have syntactic, and we have algorithmic grounding of those. And essentially, we are done. The rest is computation. Now we have a machine. We have a machine to which we can input 2 things: what we know and what we want to know. And what the logic is from going from the first to the second.
I mean, please continue.
No, this is on one level, it's a mission accomplished.
Mission accomplished. Right. So the social scientist in me and also the philosopher in me, I mean, I agree on the sense that once we have knowledge, I mean, I've used those DAGs, and I think they're to a large extent beautiful. They're very useful in bridging theory and data. Now, one critique that you might raise, or at least a reservation, is that how do we handle knowledge in when knowledge or theory is uncertain? So if you think about social sciences, where systems are complex and it's very hard to pin down the exact DAG. I mean, you could think about, and again, the DAG for the listeners are directed acyclical graphs encoding the relationship between variables. So how do we think about uncertainty, the knowledge uncertainty that encodes the DAG today? How do we handle that?
You only can put in what you do know. What you don't know remains as a partial knowledge. So we don't have the DAG. But something about the DAG we know.
We have something. Usually know something.
Just insert what you know, leave the rest to the unknown, and the outcome, your outcome, is going to be provisional. Every outcome of this exercise is provisional upon a certain assumptions. If you buy this set of assumptions, then I can tell you that this conclusion is logically implied by your input, and that's all I can give you. Input-output relation from assumption to conclusion. But the nice thing about this exercise is that I can explicate the assumptions in a nice language that you understand, and you can judge. You can judge whether they are plausible or not. That's number one. Number two, you can answer the question, do I really need those assumptions? Perhaps I can get by with less. Okay?
Right.
So these are two facilities that are important to have a complete system.
Yeah. So what you're saying, Dale, is that the language of the three level, the ladder of causation, or the DAG that we have, and is a tool for communication among scientists to say this is what I think the world should be. This is my knowledge about the world, and I'm encoding it in a DAG, and these are my results based on this data. And so we can use that language as a vehicle to communicate, to complement, well, basically English language about causality, right? I'm summarizing what you're saying here.
Yes, we have a communicable language.
Yeah.
Which that everybody understand. I'm not talking about potential outcome. I'm talking here about assumptions that I can convey, that one scientist can convey to the other and ask, do you think it's plausible? And they can judge and communicate with those assumptions.
Yeah.
Once, and they said, this is all we know. The rest we don't know. Do we have sufficient knowledge to get what we want to know? So both our knowledge and our desired conclusions are formulated formally. The rest is mechanical. Shove in what you know and get an answer. Is it sufficient to derive what you want to know, given the kind of data that is available to you?
Right, right.
And if the answer is no, then you know that nothing can be done about it. You can go to partial identifiability and say, can I have a bound on my answers? I'm not insistent on point estimate. I'll live with certain bounds. Okay,
right.
Shove it in and grind the system mechanically, and the answer will come yes or no. Answer can be even more sophisticated.
Right.
If you can only give me an experiment here or there, I can answer questions much better. So that's a sophisticated kind of system.
Right, right. I mean, it's a complementary system. So one of the I'm thinking about my own trajectory here today and into the field of causal inference. So I started off as an applied researcher and then learned a lot about applied causal inference from an econometric point of view. So the potential outcome framework, do natural experiments for identification, IVs, regression discontinuity designs, and different diff, and there are many different methods here that you can use. So my question here, and this is actually very interesting for me, then when I ventured then into computer science, only then did I discover there's a completely new land. It's complementary. It's not saying, necessarily something different.
Complementary. Yes.
It's complementary. So, and it was not until I opened up the door into computer science and saw that land of causal inference that I realized that there's a different way to think about the same problem, complementary way. So how can it be, and I believe the situation is much better, but how can it be that these two trajectories have evolved so in silos? How come that we have been sort of isolated for so long?
Oh, okay. Part of it is personalities. Part of it is professional pride. And language. Language is the hardest thing to adapt. Once you grow up in a certain language and you devote most of your career in one language, to adapt another one. I always said that people go to war on languages. They can agree on the principles. They can agree on God and not God, but not on language. They go to can agree on morality. What is God? It's just the principles of being nice to each other, right? We all agree on that. Yes. But on language, no. We'll go to war because my God is better than you. Okay. No, it's true. Learning new language is very hard.
Yeah.
So imagine the trauma of statisticians that have been invested all their career in the paradigm that the language of probability theory is the language of knowledge. Okay? Which means that everything we want to know can be expressed in probability, and statistics will give you the right connection between data and the probability distribution. That's how they grew up from Bernoulli, okay, up to Pearson, Neyman Pearson.
Fisher as well there in the middle.
Yeah. And here comes a guy, his name is Civil Right. I devote for him a whole chapter in the book of why. And he said, that's not what I want to measure. I want to know the effect of the color of the guinea pig father on the guinea pig sibling or the child. Yeah. And I want the effect. I don't want the correlation. So I am going to play God and invent a new mathematical object that no one has seen before. It's called an arrow. And I'm going to put it down, and I'm going to do my game, my play. I'm going to play with these arrows, and I'm going to get answers, and I'm going to call the answers causal effect of the father on the child. Bing. And could you imagine what the statisticians feel? This guy's crazy.
Yeah, it was a mess.
There's one language for science, and this is probability theory, okay? And here comes a guy and contaminated with arrows. We have to do something to castigate it. And they tried. But he remained convinced, and he was right. Eventually, the statistician, too, came to it. Actually, they didn't. They didn't until Rubin.
Right.
In 1974, he gave a sort of probabilistic interpretation to potential outcome.
Right.
And he delivered them from the trauma of thinking causality and thinking causality and speaking probability.
Yeah.
So he allowed them to adapt the language of probability to something that they really want to express.
Right.
I want the causal effect.
Yeah. He took it further, and this is really the fascinating. I mean, to some extent, the internet has helped us to move beyond this. The installation of disciplines in statistics against computer science, and economics against statistics and computer science, epidemiology, and so on and so forth. So you have these, if you like to call them parallel discoveries or parallel formulations. Between, say, you work in computer science, where you develop the foundations of causal inference in computer science, Ruben in statistics, Gideon Imbens later, and Josh Angrist in economics, and others obviously in following suit, epidemiology, Jamie Robbins. So how this is, there's a parallel discovery basically, and I know that some of you have been working together and talking to each other as well throughout your careers. But how is it? I mean, there are several questions here. One is the installation of discipline. How were you guys trying to make the best out of the situation to talk to each other? And also, how did you handle the disciplinary differences?
There are many issues here. First, the language barrier and the investment in language. Now, the Rubin disciples have conditioned themselves to think in terms of the potential outcome, and they find it very hard to dislodge themselves from this prison or from this handcuff. What I don't want to get into, or maybe I should get into.
That's fine. I mean, we can. I'll try to moderate as much as possible. Now, unfortunately, they're not here to reply. But I'll try my best to be the devil's advocate. But we'll invite them in future conversations. But be nice to them, please.
Yeah, I'm always nice. I'm always respect what Rubens have done to statistics. Yeah. It was a revolution. It allows them to talk about something that they want
Mm.
in terms of something that they think they know. Okay, here it's failing.
Mm.
Because people know causal relationship between variables, okay? Not potential outcomes. They don't think potential outcomes. And you want a proof of that, go to Rubin's and Imbens and Rubin's book of 2015 and look how they define confounding. Okay? You find there's 6 pages of talk of what I found to be incomprehensible talk just to define the idea of confounding.
So what was
Because
what's your main issue with the definition, just for the listeners?
The definition is built on the idea that a certain potential outcome is conditionally independent on the treatment.
Okay, so it's defined in terms of a conditional independence statement.
It depends on potential outcome.
Potential outcome statement, exactly. So it's an unobserved quantity.
Could you imagine a reader and understanding how potential outcome of a treatment can be independent of the treatment?
It is a hard thing. You need to
it's hard.
You need to train yourself to think.
Yeah, 6 pages. Okay. Now, which means what led to a whole culture where, because it's so incomprehensible, people assume away conditional ignorability as a given thing and continue with analysis as if they solve the problem. Because they don't see the actual assumptions, the real assumptions that they can communicate with. Okay? So that is something which I think is missing in the Rubin approach, the transparency of the assumptions.
Right.
And with transparency come many other things. The question of completeness. Do you know if you have a bunch of conditional independencies or ignorability conditions, conditional ignorability conditions? Can you tell if one implies the other? Can you tell if they conflict with each other? If you have enough of them to express what you really know about the world, these are all undoable. It's something beyond the capacity of every mortal.
Right. So in one in one parallel here, I see is the potential outcomes obviously coming from the potential outcome framework, and then in the language of your theory of causality in terms of counterfactuals. To a large extent, they have resemblance, but I also see that counterfactuals in your world comes from the fact that you already have a DAG that you sort of define. But so can you talk a little about the differences there?
The initial primitive upon which everything is built, it means my system, is listening. The temperature listens to the pressure listens to the radiation, and so forth. What you understand about the world, which is the way we communicate. And I've proven it by looking at some conversations among epidemiologists about the effect on blood pressure on something else. They communicate in terms of absence and presence of a certain chemicals, and whether they listen to each other, one affects the other. That's the way we think about science. We don't think in terms of potential outcome, because so the input has to be plausible. Okay. Once we have it, the rest is mechanical. Once you express the knowledge that you have in terms of who listens to whom, and then you can derive the counterfactuals from that.
Right.
And the counterfactual that I get from my mechanical system can be proven to be equivalent to Rubin's.
Right. Yeah.
Which means that if you make the same assumption, that's with different language, you guarantee to get the same conclusions.
Yeah, this is definitely some research there showing those overlaps. I mean, the quantities of interest they lead to the same conclusion. It's just that the approach is different.
The input is transparent.
Yeah, yeah. So how, I mean, I'm curious about this, going back to the question of parallel discovery or parallel development of those frameworks in statistics, econ, and so can you talk a little bit about the inception of the field and the interaction among these?
Yeah, I just tell you my experience.
Yeah, absolutely.
When I presented this kind of work in Harvard, in Rubin's group, there was total silence. Okay, no response, no traction. Okay? What is the guy talking about? Okay? Actually, statisticians at the time were divided into two groups. Some of the Rubin disciples believed that this is the last word in causality, and some of his adversaries said it's a fraud. And I have the emails with both sides. So some statisticians believe it's a fraud because you assume potential outcome, and then you get answers based on them on something you don't even understand. They call it a fraud. And so statisticians didn't understand what I am doing there. However, I had the luck of meeting Sander Greenland and Jamie Robbins and Friedman, David Friedman, in Berkeley in one time, and we started talking, and I showed them how I can derive the backdoor criterion, front door criterion, and get answers that were totally unknown at the time.
Right. Okay?
And they were excited. And Jamie even took a plane and came to California, and just to understand how the do calculus works. So, and we got a paper written in the epidemiology, the causal diagram in epidemiology.
Right. Yeah.
It's the most cited one in all my papers, not counting my books. Okay.
It's amazing. Yeah, it's an amazing take up in epidemiology.
Yeah, and epidemiologists today speak DAG as a second language. It's not something you have to teach them. They think that way, communicate that way, and operate with it. It's all
trying to publish a paper, which I've tried without having a DAG in epidemiology. You always get reviewers back asking for a DAG. So that's the standard today.
We want to know what you know. We want to know what you wish to know, and how can you express it in any other language?
Right. And so there's interactions with epidemiology with James and Greenland, Jamie Robbins and Greenland. So how you guys developed, and then that interaction seems to have been quite fruitful in many ways.
Yes.
So how were there any limits in terms of what could be taken up into the world of epidemiology versus not taken up, also in the world of computer science from epidemiology? How much interaction was there between the groups?
Well, I cannot recall any method. Yeah, I got from Jamie few ideas that I didn't know about, like the inverse probability.
Right. The
probability, yes. And yeah, so we borrowed it, and the most interaction on the methodological plane. Yes, right. Absolutely.
And then with economics, I mean, interestingly, how has that interaction been? Because in economics, the causal revolution happened more or less in the 90s. It started to really rise with the...
In economics?
Yeah, in economics, with the publication of...
Economics is the whole new animal. The professional pride is extreme, is an obsession. And you wouldn't get any economist to admit that he or she learned anything from any other field. That's a no-no. That everything was done by some economist, from Marshall until Habermas. And indeed, they did a lot of pioneering work. Habermas was the first to say the structural equations, which were used routinely by economists, are none other by description of a hypothetical experiment. That was Habermas' idea.
Right.
And after him came Strauss and Wald, who said, if it is, then let us just eliminate the equations from the structural equation and get the result to intervention.
Yeah.
We just replace the equation by a constant. That was another economical idea by economists. And then came Spiritus and Clark, and they translated the surgery on equation to a surgery on a graph.
Right.
You simply cut the input errors. And this is why I remember Uppsala, because it was in the Congress in Uppsala in 1991.
What Congress? One Congress?
Congress of Philosophy of Science, I believe.
Okay.
And I sat in the lecture where Spiritus gave his cutting of the errors there.
Yeah.
And I said, wow, we now have a calculus for intervention.
Okay? Interesting. So that's where you got the idea of mutilating. Okay.
Of mutilating, yes, the graph.
Yeah.
And then in 1993, it translated into a backdoor criterion.
Right.
The backdoor criterion for choosing the right set of covariates in order to emulate an intervention.
It sounds, I mean, I'm gathering from what you're saying is that the inspiration to your work is coming to some extent from collaboration with EPI, but also with philosophy of science and the mutilation of DAGs, as we say in the Uppsala conference, philosophy of science. But statistics and econ has been maybe less receptive, but also an important partner, I assume, in terms of conversing about how to develop the causal inferential framework, the toolkit.
The economist?
Yeah. Oh, econ and statistics. I mean, with Donald Rubin, even if the reception was...
The reception remains strange estrangement, non-responsive, ridicule sometimes, but no, I cannot say. The statisticians remain foreigners, aliens, and the economists even more so, because they have the problem of professional pride. So
yeah, I mean, one thing that I'm thinking about today is really the I mean, for example, the natural experimental toolkit that largely comes from economics with IVs and regression discontinuity designs and so on that are a complementary toolkit. So how do you think about those methods in the causal inference landscape and contributions from econ into say computer science?
I regard them as special cases of do calculus, in the sense that you have a DAG, you have to start with some assumption, exclusion restrictions and exogeneity. You have to start with assumptions, and part of your tools is can you get from these assumptions to a conclusion? And the answer is yes. If you sacrifice average causal effect and you settle for late, then you can get it. Okay? Right. It's a proof in the calculus of counterfactuals.
That's actually really fascinating. So it'd be fantastic maybe for the audience if you have some recommendations for reading and the overlap between natural experiments and thinking in terms of DAG. How to do that translation, because that's a way.
We have a paper in 2001, I believe, with Brito about. I talked with you about it before the lecture, before the interview, about turning a bad IV into a good IV by conditioning, or choosing IVs correctly, or in linear system, equipping them with greater power of inference. Yeah. So we can embellish a model with IV with ideas from DAGs in order to get a greater power. Yes, we can do that.
And also the IB has a natural, at least in my mind of how I think about it, a natural overlap into the DAG world. But if we think about, for example, difference and difference, that has more of a sort of a linear trend assumption identification. So how do we think about that, for example, in the DAG?
I consider it to be a special case where you have equality assumptions. The assumptions between two time slots. You have you have equality constraints between the causal effect before the transition and the causal effect after. Once you introduce the equality constraints, and we have a paper on that, then it follows up also automatically.
Yeah, is that the same paper? It would be fantastic for the readers to for the
No,
listeners.
it's a different paper. It's about the equality constraints.
Okay, so perhaps I'll follow up after the conversation where you can send us some link. I'm happy to put it in the description of the video.
Okay.
To follow up on that, because I believe there's a lot to do in terms of reaching out to the field of economics, where applied research is really one of the applied causal inferential research is one of the core sort of benchmarks. And one way to reach out to that audience is to start talking about, the methods that they tend to use, the identifications that they tend to use, and then show exactly how that sort of maps on to the DAG world. I mean, that's at least one bridge.
Well, the main connection is making the assumptions explicit and plausible and transparent.
Yeah.
So you can use whatever method you want, but make the assumption transparent.
Yeah, yeah.
I don't know any other vehicle to make them transparent except for the DAG, because you say who's listening to whom. That's how the mind works. Yeah. That's how we think about the world.
It's a theoretic. I mean, it's a bridge, sort of a bridge between the world of theory, the English language world, and the data world, and so that way helps.
Correct. Between the way we think about the world, and the way we deal with what we deal with it formally.
Yeah. So where does please, Judea.
No, so my effort has been to take the knowledge in its natural habitat, express it in the way that you think, the way you explain it to your colleagues in the cafeteria. Take that knowledge and make it the basis of the starting point. Okay? Don't force yourself to molest your thinking to fit them into a demand of the formal language. Like potential outcome. Don't force yourself. Talk the way you talk normally. The system will take and translate it correctly into whatever is needed. Counterfactual, backdoor, everything was done mechanically. That's where the computer science comes in. Maximize the mechanical part and make it easy for people to express themselves and to express what they really want.
So two sets of questions before we move on to other topics here today. One is the relationship to sociology and political science that came after the revolution that happened in computer science, statistics, and econ. Political science probably a little before, with Gary King amongst the leading figures, and others in political science, and sociology, Chris Winship, and amongst others, to mention some. So where do you see their place in the development of these ideas, and also maybe moving forward? Where do you see them going?
The book by Morgan and Winship was very influential, I believe, in sociology or social science. I think so. And I was very happy to see it coming out. It had all the DAG's tools, and it had the potential outcome and a counterfactual.
Right.
But it has one missing link, which I told Chris, which is it could be detrimental.
It could be what? Which one? Yeah, what was the link? What's the missing link?
Detrimental to the reader.
Yeah, what's the missing link?
The book is divided into two parts. One is potential outcome and counterfactual, and the other one is DAG tools. And it doesn't say that the potential out can be derived from the DAG.
Mm.
So if you really want to compute a counterfactual statement, such as if I hadn't done it, then it wouldn't have occurred. If you want to derive an answer to that, where do you go? You go to potential outcome? No. I go to the DAG because I can derive it. Right. I can derive all the things that people in potential outcome labor to achieve from something simple, a DAG. That is a missing link.
All right. So, well, we'll pass it. We can pass that on to Chris. I mean, he's actually.
No, I did already. I did already, and he admitted that this is an important link that can be repaired in 2 pages.
Yeah, and I mean, a lot of the conversations between econ and also this natural experience could be clarified. I think creating these divisions between chapters can be also detrimental in the way that you can show how one and the other is sort of related to each other. And
it would be nice, to work an example in both representations side by side.
Yeah, exactly, to show how they complement each other.
That would be a tremendous help.
Yeah. So that's interesting. So where do you and maybe we can move a little bit further here in terms of the questions and relationships to AI, development of artificial general intelligence and causal inference. I know that you are a proponent of bringing causal inference as one of the critical components of developing a general tool for understanding. And not only that, a sort of a development of AGI. So let's start with just a metaphor, right? Maybe an interesting sort of maybe provocative idea. So we have self-driving cars today, Judea Pearl. We have self-driving cars. We have them. They're not everywhere, but technically it's almost solved. There are some limitations. Now, what if we think about the same parallel and think about a world where there are data collections and sensors where citizens of a nation can push their wants and needs and concerns to the politicians, and through that sort of linking it to a algorithm, a general algorithm that can sense what's going on in the society. So can we think about a self-driving government in this sense? Can we, in a future world inspired by self-driving cars, think about a entity like that could assist decision making on a societal level? And is that something? I mean, there are ethical issues obviously here, but I'm just talking about the potential of that mechanism. So how do we also integrate causal inference into that sort of?
Two questions here.
Yeah,
two questions. How to integrate causal inference, and whether the future is promising us to have a programmable government.
Exactly. 2 questions.
Okay, yeah. But the first one is, so far, deep learning and big data, machine learning are not introducing causal knowledge into their system. So self-driving cars are still operating in level 1 and maybe 1.5. Because they're using RL.
Reinforcement learning.
Reinforcing learning, okay? Reinforcing learning, you have actions. You do take actions, and you look at the consequence, long-range consequence, and you modify you make conclusion on that basis. So you have the input already in the form of experimentation. It still doesn't give you into level 2, which is the full do calculus. It has some missing part, and but it's a beginning. So you have a 1.5. We still have 3 levels to climb before we get into understanding. And definitely you cannot go into level 3, which is imagination and counterfactual causes of effect, as opposed to effect of causes. That's explanations. So the systems suffer from inability to explain themselves, inability to transfer knowledge from one domain to another.
Right.
It's also the feature of level 3. And so it's limited, and we have to be aware of the limitation. And we have the science now to tell us what assumptions or what input information is needed in order to overcome the limitation that we have today.
Right, right.
How to do it? I think that the essential to equip robots with the template, like a DAG, okay? A template as a bait. This is what you have to get. Not the DAG itself, but the idea that until you have a DAG, you haven't finished. You should continue to experiment. You should continue to manipulate. You should continue to playfully manipulate things until you get. This is what we find in babies.
Right. They learn by experimenting with the world.
Playfully.
Playfully.
So it's important.
Yeah.
Not because they are enticed by reward.
No, that's right.
It's reward neutral curiosity.
Yeah, yeah.
The babies are rested until they understand why one toy makes a rattling noise and the other one doesn't. And they keep on experimenting until they find out, oh, this has a ball inside and this one doesn't, okay? You don't find in monkey that kind of reward neutral curiosity. So a machine must be equipped with that restlessness.
Yeah, exactly. So the self-driving government needs to have obviously a higher level of imagination.
Now we go to self-driving government.
So is that possible? So imagine the data was there. Everyone had can put in what they want and so on, and the, I mean, whatever data you need, you have it. What are the prospects to have a self-driving government?
I'm not a speculator. I really, it's doable. I know it's doable because we have a blueprint and the logic to do it. How dangerous it is, I cannot speculate now.
No, I mean, danger, but I totally agree. I think that's a different question. Right now, I'm just playing with the idea as towards the general AI.
You have to put checks and balances, because what would prevent from powerful corporations to hire programmers and duplicate their input as if there were 3 million people demanding a certain resource? Okay,
right? Yeah,
you have to guard against that. It's easily hijacked.
Yeah. And it also needs to be probably, I mean, there are ways of doing this. You might need to have a conservative AI, you need to have a left-leaning liberal AI, depending how people think in terms of values. Because I think probably the critical piece that is missing today is values. What is the value of the ideology of I mean, human beings have values, right? I mean, but
a machine can have values too.
Their value is to maximize reward, right? Minimize error.
We can program utility because of objective functions, utility. Okay. Yeah. Hopefully, the utility should be our utility.
But that's what I mean. It could be if you are a utilitarian, you give it, say maximize reward. But if you are not a utilitarian, maybe you're Rawlsian, saying, okay, so I don't care about maximum utility. I care about everyone's starting off with the same amount of resources when they are born, but then I accept inequality as we move forward. So in that sense, you need to program in different philosophies, different ideologies into.
Well, I think the value that we have, including non-utilitarians, are really condensation or abstractions of long-term utility.
Yeah.
Long-term. When you think long term, then even God becomes a value.
Yeah. And we can teach it perhaps to have religious values or non-religious secular values and
sure. And we find the religious motivation in every tribe on this globe, on this planet, right? Which means evolution found some survival value in that hypothesis. And the robot will find it too. Because if we program it to strive for explanatory system, a template that can explain, the robot will immediately invent God. How else can you explain that the righteous one suffers and the evil one succeeds? How can you explain that?
Yeah, I mean, these are some of the most critical social scientific questions, how societies form and how to organize. I mean, definitely in the past, ideas about God and whatnot, even democracy is a way of organizing, a value system that we have put forth to organize ourselves and defend with our lives. And so perhaps, if I'm a new a researcher entering the field now today it could be AI, it could be causal inference, what are the major questions that you see are open that we should where should we move?
I have a few pet projects that I think are ready to be algorithmized. One of them is easy to understand, is personalized decision making, personalized medicine, because that requires counterfactual logic.
Right.
Find what is the probability of harm and probability of benefit for you as individual, as a patient, not for population. To go from population to individual basis, okay? And that requires counterfactual logic, and we have the logic, so why not do it?
Right. Interesting. So what counterfactual inference is one big question that you think is an open avenue.
And to implement it in applications such as personalized medicine, and perhaps even in political science.
Yeah, perhaps personalized public policy. I mean, personalized social policy. You can think about ways of personalizing many things.
Yeah, it's dangerous too. Fine.
True. I mean, there are dangers, but it sounds like ethics is something you care about as well here. So maybe the fairness ethical literature on AI and causal inference is another.
It's another area where counterfactual logic plays a role. So these are applications. Plus, I have a pet project in social intelligence.
Interesting. What does that mean?
It means that we want to have robots communicating with the user with vocabulary such as "I care for you," trust me. Don't you think I'm trustable? Haven't I been good to you? And so to build up a emotional understanding and compassion and a feeling of trust.
That's amazing. Okay, that's really so basically how you build in trust into the system of algorithms.
A system of robots. Let's start with the robots, okay?
Yeah.
Would they be able to perform better once they build up internal trust between members of the community? We do it, you see. And the reason, look, society which are built on common values, they generate trust among people, and they function better than societies which do not have this commonality of values.
Yeah, trust is actually one of the more fundamental factors determining development of a nation. If we trust each other, it's much easier to do business, much easier to handle affairs of where we differ and agree. And so trust has to be one critical factor, and the absence of corruption in that sense, because if you...
And sometimes it's just a matter of, oh, you are from Wisconsin, so you must know so-and-so. Yes, we are friends.
Right, exactly, yeah. There you go. And so that's really fascinating. So then counterfactuals, social intelligence system, and anything else that you think are
Free will. That's the last one.
right, which I know you have ideas about being deterministic. There's no free will. Have you changed your mind?
We want to program in free will, so we bring this free will philosophical question to its end, to a natural conclusion, which means program it.
That's amazing. I mean that's something I really looking forward to hear. So what's the okay, but in terms of causal inference, it sounds like the field has been going on for a while now, and that there are obviously a lot of questions that were open that are now well researched. There is where do you see anything going on there in terms of if anyone in causal inference are listening to this and AI, where do you see open questions that are with big yields?
Big questions?
Or are they all tapped out?
One question that came in recent weeks was how you can combine results of experiments with observational studies to improve something, to answer questions that each component in isolation cannot answer alone. Suppose I give you both observational studies and results of experiments, RCT. Okay? Can you answer questions that you couldn't answer with each one of them alone? What question can you do? Look, we have here a dilemma. We have cheap data available from observational studies. Lots of it. A lot of data, and it's cheap, and it is collected at its natural habitat.
Right.
And on the other hand, but it's contaminated with confounding. On the other hand, you have a non-confounding data coming from RCTs, very expensive, contaminated with selection bias, okay, and things like that. Can you combine the two to get something which each component by itself cannot answer?
Right. So transferability of results or transportability.
We have answered some of the transportability results fairly completely, very completely in a way. Yeah, we have, because we have a completeness result for some of the transportability questions. But these are one area where we can answer is personalized decision making. Those cannot be answered with each component alone. I give you an example. If you have an RCT result of RCT, and you find an experiment which in which 10% die, and on both treatment and control, you don't know if this drug, is totally ineffective, totally ineffective to any individual, or it kills 10% and cures 10%. There's no way to determine it by the RCT alone, because it's a population data.
Right.
You don't know if you have even a single individual that would have been cured had he not taken the drug.
Exactly. There's other half is missing, basically.
You cannot determine. But if you have a combination of observational data and RCT, you can tell. You can put bound on the probability of benefit and probability of harm to individual.
Right. That's then assuming that the RCT is operating under the same DAG as
on the same. Not forget that, on population.
The same population, exactly. Yeah. But there's a stationarity in the system, that no arrows have changed direction or anything like basically there's.
Look, you have population that are eating sugar or eating or exercising on their own volition.
I see. So it's basically drawing a sample, running an RCT on the sample, and then
right. That's right.
Okay. Yeah.
Yes.
Yeah.
The combination gives you more than each component by itself.
Right, I see. Well, that's fascinating, and there's a lot to be done here also in open RCTs, basically RCTs on an open systems, but also in laboratories where you might say that you're taking the people out of their natural habitat, so the system is operating slightly differently. So
that we call it selection bias.
yeah,
So
right.
the people that are selected for the
Selected
RCT have to sign agreement, and they have to find permission slips from their parents. There are different kind of, and they are incentivized by the condition of the studies.
Yeah.
They are mostly students or homeless people, which are different than the population at large.
Yeah. So there's so many fascinating ideas here, and I'm changing gears a little bit here into your macro strategies, Judea, in terms of your energy levels. Like, you have so much energy, you have so many ideas, you're working on so many different things.
Well, you caught me in the time that I'm working at 1 a.m. and catch me in the morning and I'll be a zombie.
Exactly. Well, that's the fascinating part of this conversation, is that you for the audience, is that this is morning now in Sweden, and Judea's calling in from, I don't know, it's like 2 a.m. now or something, 2:30.
It's 2:30 a.m. Yeah.
Yeah, something like that. So, and this is the natural time that you work.
Yeah.
So managing your energy and time for, have you always been like this, working in late nights? Is that the natural?
It's natural. Yes, I've been doing it for 2 or 3 decades. Yeah.
Wow. Okay. 2, 3 decades. And this is, so when you, let me think back, I'm thinking about when your kids were still small at home. I mean, they had to go to school. I mean, I guess that was a different ball. This is before,
Yeah, different
this is
generation.
after
Yeah.
they grew up. Okay. Okay.
Right.
So why is this a good time? Why is this like, why is night a good time for you to work? Do you think? What's your?
I suffer from a tremendous pressure when I know that somebody sends me a message and you expect a reply. It really kills my ability to think. But here at night, I know that no one expects me to answer. Right?
I see. Okay, so
they forgive me until the morning.
That's amazing. So it's all the emailing that's pushing your all the demands on your time that push you keep on answering emails, and then you start working seriously when the emails quiet down.
Yeah, when no one is being disappointed by my work, then I can work.
That's amazing. So you are in that sense very caring about what people, to really get back to people. And I mean, actually, just scheduling this interview was quite quick, because you answered quickly, you replied, and there was a fairly smooth process, which is unusual for people busy as you are.
I love this conversation.
Me too. And so, but thinking about deep work, Judea. So, okay, so you do the deep, like, what's the amount of, I mean, because a lot of the work that you're doing is non-experimental in the sense that you're not running a lab where you do. Correct. You don't do you do some programming, but it's really the formalism, the math that you are thinking about the idea. So can you walk the audience through the usual mechanics of a paper that you love and admire? Like, you have so many of them, but just take an average paper that you love. How do you think, how the process of working through a paper here?
First comes the question, can we do it? Can I do something today that I couldn't do yesterday? Or will I be, if I solve this problem, will I be able to do something that I cannot do today? Which, take for instance, the back door criteria. Okay. The question was, come on, guys, we have to find out what to condition on so that we can guarantee that we have that the result of the conditioning operation will be what we asked, and we asked for the causal effect.
Yeah.
So,
yeah.
So I submitted to my calculus,
mm,
and I say, can we say something about it?
mm,
And the mathematics give me the answer. It's the
mm,
greatest pleasure in the world.
mm.
Submit it to machine. The
Yeah,
machine gives you answer,
yeah.
and you know it's right. It's not like GPT, right?
No,
Because
it's not.
GPT
It's very
can
different,
cheat
right?
you. Right. You submit it to mathematics, and you have guarantees.
Yeah. But even if we go back, so the do calculus gave you a language to do this, but let's go back to even a harder question. How did you even come up with the do calculus? What was the process of discovery, the process of formulation?
The process comes from computer science. If you have semantics, you should have a calculus. If you have semantics for a concept, intervention, for instance,
Hmm.
it's okay, I have a semantic for that. I
Hmm.
have a model. I know what it means to intervene on a variable.
Hmm.
Okay? I can derive the consequence of intervening.
But
And
how did
now
you even know? Sorry to interrupt you. How did you even know that intervention means doing this mutual? Like
that
it's
was from Spiritus. I told you. In
right.
Oops,
I know. But before that, you must have gone through and just thought, how do I encode this idea I have that I'm calling intervention in this particular way? Because in the beginning, it's very hard to even.
no. First of all, I was wrong for about 10 years. I thought that Bayesian networks,
Hmm.
probabilistic Bayesian network, have
Yeah.
an answer to all the questions in the world.
Hmm.
I was as misled as statisticians are. That
You're blaming them again, Judea.
no, that probability theory answered the question that all the questions in the world.
Yeah, yeah.
And I believe that causality is just a shorthand notation for some pattern of independencies.
Okay, that's a very good example. So how did you lift yourself out of that spell?
By I already okay. First of all, I noticed that in the Bayesian network schemes,
Mm,
people who have been using the Bayesian networks
mm,
always put the effect as the children of the causes. They
mm.
didn't have to. They didn't have to,
Okay.
but they did.
Mm,
And when I asked them why is it so, why do we get this convention
mm,
of putting the causes as children and
mm,
not the other way around,
mm,
they gave me a very strange answer.
mm.
Very strange. It's easy to reconfigure it.
Okay, interesting.
No, really, it came from Microsoft.
Mm,
They built a Bayesian network diagnosis system
mm.
to diagnose the trouble in a car, for instance.
Right. Okay.
Okay, so you have a new model of the car, a new water pump.
Mm,
Now, do you need to rewrite the whole expert system of diagnosis from fresh?
mm,
No, you
mm,
keep the entire DAG intact,
mm,
and you only change the water pump
mm.
characteristics. Okay?
Right.
All the rest remain the same.
Mm.
And you can only do it if you have it organized cause and effect.
I see.
Because then you utilize the modularity idea of cause and effect.
Right. So there was some kind of a dissonance in your mind about how they were doing things
And
that
why they're doing it.
yeah, and they prompted you to start thinking about there must
Then I
be a
start
better way of
thinking
doing this.
there must be something to causality which
Yeah.
is more than just a pattern, a shorthand notation for
Right.
patterns of independencies. Yeah.
Mm, mm,
So I knew that causality plays important role. I couldn't capture it, and then came Spiritus' idea about cutting errors,
right.
which came from the economist of cutting equations.
Mm. Oh, I see. Interesting. Okay, I see. So you put them the two together, and then you had the idea of a do operator.
Or do operator.
Yeah.
But now comes the second one. As a computer scientist, I'm not satisfied with do operator.
Mm,
If I have an operator, I should have a calculus for this operator. What does it mean? So from a collection of do expressions, I should be able to derive another do expression.
mm.
which is logically implied by the first,
Mm.
but it's a different kind of do operator.
Yeah, I mean, the do operator is basically a verb saying, yeah, if it takes an input and out comes a output, which is a intervened DAG, basically something
Which is the probability distribution of the outcome,
yeah,
given that you perform this experiment.
exactly. And so the whole do calculus was basically then. So walk us through that. So how did that go about?
Okay, now you suppose I'll give you an example. It wasn't chronologically the example that drove it, but I'll give you an example. But do calculus. Suppose you cannot. Some variables are manipulable and some are not in your system. And you want an answer, the causal effect of X on Y, but X is not manipulable. But you have some other variable, Z. Z is manipulable. Can you get the answer to the question? What's the probability of Y given that I do X, but doing only experiment on Z? X must remain untouched.
I see, okay.
Now you can see what I'm looking for. I'm looking for expressions which involve do Z only. That will be a consequence of expression. Oh, sorry. The output should be do X, but it will be a derivative of expression that involves only do Z. These are the experiments on Z, giving me the conclusion that I need. What will happen if I do X? And I never do experiment on X.
Yeah.
I only do experiment on Z.
And so this was a logical follow-up from the fact that you wanted to make make Bayesian networks much more tuned towards causality, and hence the DAG framework. And then
I interpret already the Bayesian network as to be causal.
Exactly. I mean, it was basically a development of it.
But it still doesn't answer the question that we want.
Exactly.
I have now I want to ask a different question.
Yeah.
I give you some experiment. Give me the result of another experiment which I haven't performed. Which means I want do expression to be a consequence, a logical consequence of a collection of do expressions. That is a do calculus.
Yeah. Yeah, the beauty of it is that you actually maintain the idea of, obviously you use probability to express this new joint distribution. So you managed to maintain the language of statistics, but you mutated it. Basically, you evolved it into do calculus. You brought it in under a new machinery.
You say it's a language of statistics augmented with another operator.
Exactly.
I see it as it's a new calculus which has statistics on the lowest level.
Yeah, but the beauty of it, and I think why there was so much of a take up, and this is my hypothesis, I might be wrong, is that why do calculus and causal inference as you developed it became so successful is that people already knew how to handle statistical quantities, right? And so you didn't
Yeah,
so it was for them to understand how to couple it with the language that you were developing. And so by having that bridge developed and set, it was quite easy for people once they understood it to start using it.
We remained in the realm of probability.
Yeah.
The outcome was probability of output, given that you do something, still probability.
Right.
So that helped people. Also, we took all the tools that we developed for Bayesian networks, like disseparation. That was developed in a totally probabilistic domain, nothing to do with causality.
Interesting. Yeah, that stands for dependence or independence in terms of relationship of variables.
To find out if X and Y are dependent or independent, given that we condition on a set of Z.
Right. Yeah. Right.
Find out yes or no. Give me a yes or no answer.
Yeah. And so, zooming back, okay, so now I see the development of your the moment of discovery, basically what you were after. And so how did you organize your how did you work with your collaborators to make to convey these ideas and make I mean, essentially, how do you tackle that collaborative effort as you go about developing this language?
My collaboration was mostly with my students.
Right.
And to my students, it was very easy to convey. Suppose we know only that. Can we still derive that? Find out. Okay,
okay, so they went off basically and worked.
Yeah, find out and come and see me in 2 months. Oh, don't call me until you have a breakthrough.
So that was my question. How do you actually collaborate? But I see. So basically, you give them this hard question, and then you let them be for whatever time they need. But
yeah, cool. Some of them are actually, as I explained in the book of why, some of the most significant progress they did on their own against my advice.
Right. I know that, for example, Ilya Spitzer is one
right.
worked quite intensely with. So you didn't do like the weekly meeting stuff. You didn't meet students every week and help them,
no.
Give them feedback, help them accountable, set goals.
No, we didn't have that. At one point, we had a weekly seminar, in which we invited people from Caltech.
Yeah.
And we just kicked ideas.
Okay.
But that lasted about 6 months. The traffic was too hard for them.
Yeah, traffic in Los Angeles is not the easiest. But so is this the mode of collaboration that you tend to find yourself in, Judea? Is that you sort of formulate the problem, you work with students, you let them work hard with it, and then come back. And we're talking students that are graduate students, so they're doing their PhDs.
Graduate,
not master students necessarily only, or bachelor.
Many PhDs.
PhDs, yeah. So they were formulating. And so were there any, I guess, like at some point you sit in front of the whiteboard and just derive the quantities and you question them and you develop the ideas together through that questioning.
I pose a question.
Yeah.
Is it possible to do? Yeah. In mathematics, it's very nice because the questions are always, is it possible or is it not possible? Given that I assume that, is it something possible or not? So the answer is yes or why. We are yes or no.
Yeah, that's the beauty of mathematics. It's easy in that sense. And so, thinking about leadership, you're also the director of the Cognitive System Lab at UCLA. So how did you manage your research simultaneously as you were directing that laboratory?
That is my lab, my interaction with students.
That's how. That's
you don't have a lab if you envision a chemical laboratory. You don't have that.
So why is it not called the Causal Inference Lab? Like what's the? I know that cognition is part of decision making, obviously, right? And that's a critical piece.
Yeah, but it's a bigger part. It's a bigger name. It's a broader field. I'm interested after cognition to understand how we think.
Yeah.
Causal is one component in that. We started with uncertainty, and now we are in causal, and now we're actually doing counterfactual. We are doing deep understanding, according to my definition.
I see. So you're going into the behavioral side in that way. So it's behavioral at the robotic social intelligence side.
The question comes from the behavioral side.
Right.
How is it possible for people to do X, Y, Z?
Yeah.
Why they cannot do on a machine?
Right. And so an actual question here: have you do you work with psychologists or behavioral scientists or sociologists to actually bring these ideas into the framework that we're discussing right now?
Very tenuously. I of course read all the papers by Kahneman and Tversky, and that was even earlier when we were doing decision analysis.
Right.
In the early day of utility theory, multi-attribute utility, and prospect theory.
Exactly.
So I read this work, yes, on the behavioral side. With the Department of Psychology, I have a very tenuous relationship.
Okay.
Uh,
How come? Is it just because you have different philosophies of what to prioritize or what?
Partly, yes. They have been deeply entrenched in structural equation model with
Right.
Peter Bentler and
Mm,
his culture.
mm.
And it's a different culture.
It's a different culture. I mean, this is some of the challenges of interdisciplinarity is how to overcome these cultures. But when you do that, you can do major breakthroughs in terms of answering all
You're right.
questions.
Yes. Yes. I cannot, however, pin down what I learned from them.
Mm.
What I learned. Right. I hope they learn something from me.
Yeah, yeah. So if you have a student then coming into this field, what skills do you think they should have? Like, how do you build mastery, basically? How do you build mastery in this field of causal inference and perhaps the overlap to AI? So where do you see the skills necessary to be built for someone going into this field?
You read the Book of Why, and then you read the primer. The primer is also a good one.
Mm,
And then you read the causality book.
mm.
And I think you are ready to step in,
You're ready to go, right?
ready to go.
And so that gives you the formalism. Do you need to study deep learning? Do you need to study computer science in general to complement your skill?
I advise against it
Mm,
because people, once they get into the deep learning, they forget about the basics, that we are there not to predict and not to fit functions
mm,
and not to extrapolate and not to worry about overfitting. That's secondary.
mm,
Our job is to understand, and
mm,
understanding implies certain things.
mm, mm,
Um, it's a very bad habit to get into machine learning today because it's enticing.
mm,
You get involved. You speak in terms of the mechanics of the neural nets, what you do to them. If
mm.
you transform them from the right or from the left, you do a tensor. Who cares? Look at the purpose.
Right.
Just all you're doing is fitting functions, right?
Yeah. Yeah. Exactly. I mean, that's estimation, right? So estimation becomes in your
Yeah,
perspective, it's a secondary thing. Identification is
it's
more.
very important.
Yeah.
It's very important, but you have to place it in its right position.
Mm. Yeah. I mean,
It's a
perhaps
very
overlap
look.
between it. Where if you're interested in implementing some of the ideas that are many good ideas in causal inference that are not programmed yet, so they can be programmable.
Programmable, and once you get the estimand
Mm,
and you have a probabilistic functional that you need to estimate,
mm,
then you go and you have a finite data and you have to estimate it. You have
mm,
to be an estimator.
yeah. Mm,
And that is a function of machine learning.
mm, mm.
But we know exactly where to position it.
Right, right. Interesting. Okay, so read the book of why, causality, and the primer.
Read the Book of Why, then primer,
Yeah.
and then causality.
And I assume some basic probability. I mean, actually, in the book you do have a couple of chapters on it, but to really get good, you need to have some more formalism, I guess, under your belt. Or is it fine? You just saying no, you go for it. These are the books you need.
Well, we have a couple of chapters to bring up people who just know basic probability,
Right. Yeah. That's the
going
first part of the book.
through regression, best fit.
Mm,
And once you get into regression, then comes the graph. The graph is just a way of articulating conditional independencies
yeah. Yeah.
and variables. Once you get the tools of the graph, and how else can you think without a graph?
Yeah. This goes back to the early part of this conversation of the graph being being the bridge, exactly.
Yes.
Yeah, please.
I'm handicapped. I cannot think without the graph now.
I mean, well, once you get into it, it's very hard to not think. At least
It's
if you
very
have
hard
the
not to
theory.
think.
Yeah, yeah. I mean, it's. I'm saying this from a point of view of being taught in sociology, where we have many theories, but very little data, or unclear formalism in terms of how to actually think about the bridge between data and theory. And so in sociology and also in epidemiology, DAGs do actually play a lot of role to facilitate language. And so, yeah, this is critical.
Simply to clarify to yourself what you know and what you don't know.
Yeah.
What assumptions are defensible on scientific ground, and which assumptions are you hesitate about. You put
Yeah.
it down on graph, and you can mark it. I'm not sure about this error. I'm not sure about this lack of error, because the lack of errors are where the assumptions are.
Right. Yeah, I mean this, and then I was going to ask, but we have already talked about this of the major questions open, but in terms of in causal inference and AI, and perhaps I know that we're running out of time also in terms of your time. You need to rest, but I think that maybe it's the middle of the day for you in terms of your mental.
No, I need to. Oh, in about 5 minutes.
Yes, we'll definitely have to wrap it up.
Hours.
Maybe we do the following set of questions here into, well, actually the last ending question, Judea, is the given that you are at the level where you are and the stature that you've reached, and you see a lot in your life in terms of trajectories in academia, family, and so on. What advice would you want to pass to people? Now, this is life advice in general. How should we approach struggles? This is hard to encode in one sentence, but just to give a little bit of perspective, right? Science is embedded in life.
Yeah. I have one advice which got me many enemies, and this is rebel against your professors.
Rebel against professors. Okay.
Yes, I mean, don't take their word as the last to replace explanation. If you insist on understanding things your way, and don't take their word to be their authority to be a replacement for explanation. You need to understand it your way. And I grew up with that kind of chutzpah, with that kind of audacity to demand understanding in real time. And people here are too polite to professors.
You are, yeah. So your students, do they rebel against you?
I hope they do. I tell them, please.
And you certainly rebel against your professors and your mentors. That's
Not really, not really, not really. I did against my American professors, yes, but not in Israel. No, I wonder why. Oh yes, in some cases, I remember it very clearly. When we didn't understand in real time, we started moving our chairs to make noise to let the professors know that we lost him. And he repeat.
Oh, that's interesting. That's a social cue to make him, yeah, or her. So you have achieved a lot today in terms of what success and influence. And so you are not relaxing, definitely. You're seeing the publication stream and the citations. Things are still exploding. There's still exponential growth. What have you not achieved yet? What are you unhappy about? What is driving you?
I still don't know many things. I do not know how the evolutionary function of the illusion of free will.
Free will.
I don't understand free will. Yeah,
that's something that keeps
on bugging me, and also social intelligence. That's part of it, and many things I don't know about. But intelligent machine. When I say intelligent machine, I really mean me. I really mean I don't know how I do what I do.
Right.
and I will only know that if I see it, I can program it.
Mm.
And so there are many puzzles, and everybody wants to understand himself or herself.
Yeah,
This
definitely.
is a natural.
That's why some of us study psychology or behavioral science is to understand us in society.
They should come to they should come to computer science. Because there is no understanding except programming yourself, emulating yourself.
We definitely need more programming into the social sciences. So one
No,
last
just to test your ideas. It's a
Yeah.
laboratory for testing ideas.
Mm.
We have a laboratory for thinking, a laboratory for understanding. So if a philosopher comes to me from 15th century and say understanding is XYZ, I say, here's a laboratory. Prove it.
So how do they prove that? So basically mathematically or
So if you have a theory of understanding,
yeah,
write a program that exhibit understanding according to your criterion. Okay.
I see. Okay.
I'll give it a story and asking a question and see if it answers correctly according to your definition of understanding.
Right, and that's now touching on the question of AI and causal inference again.
Situation because I've cheated. I've defined understanding in terms of the three operations which I know how to do, namely prediction, intervention, and counterfactual. If somebody comes to me and say it's insufficient, it needs to have another layer, I would be open-minded. Tell me.
Yeah. So some of my colleagues say, understanding is really expectation. So knowing that something will happen. So if I understand that a system works like it does, if the system is behaving in terms of how I'm expecting it to behave.
But what about explanation? What about credit and blame? Okay. Are you the accused responsible for this death? This is understanding, yeah. Look at what judges do in a court. They have to listen to stories, listen to evidence, and come out with a hard decision. The guy wasn't responsible.
Yeah. Yeah. So explanation remains a critical piece here in the story.
Explanation, yeah, it's a critical piece, and that requires counterfactual logic.
So in terms of legacy, you definitely have a very explicit legacy already. What legacy do you hope, hopefully we'll have you many more years around Judea for many more decades, but what do you hope this legacy will be?
I already wrote my tombstone.
You have? that's what is it?
The fundamental equations of causation, which is counterfactual equal to a certain operator on the system.
So basically, do operator, but basically in terms of counterfactual.
In counterfactual, yes. Every counterfactual had a truth value given the causal model.
So you actually have an image already done, like the two?
Yes, yes, already. I don't have a stone yet, but I have an image.
Well, that's a sober way of seeing life, and actually. So, ending question today. I really don't want to end this, but we need to end. You need to go to bed. What's your challenge to the viewer listening to this? And this is the ending challenge that you get, the ending encouragement, perhaps, for the listeners. What do you like them to do more of and less of?
In terms of your listeners, I really like to establish a tighter communication. So I'll read your papers and you read my papers. So we understand. I understand your problem, and you understand my problem better. Right now, there is a curtain between us because most of your readers are hooked into the potential outcome thing, and not all of them understand DAGs. So this is a curtain of language, and I would like to remove it.
Mm.
I
Let's work hard to accomplish that, Judea. It has been a true pleasure having you on the show. Again,
thank you, Adel.
I don't want to really end this, but it's amazing, and perhaps we'll have you in the near future to talk about other matters that never got a chance to be discussed.
Anytime, Adel. Thank you very much for having me and giving me a chance to talk to the audience, which I don't get. Such chances I rarely get, really.
Thank you, Judea. This is amazing. It's our pleasure to have you.
Thanks.